Hey guys, my name is Hamza. I'm going to be going over a bunch of different build techniques and tips that I might have. I've learned these items over a course of 11 years of doing robotics, so hopefully some of my experience in these items might be able to give you a little bit of insight as to what could be beneficial for you and your team over this upcoming season. Now, the first thing I want to cover in today's video is I want to be talking about the basics of a drivetrain and some building techniques that you might be able to use to make some awesome drives. Now, the very first thing that you want to do is figure out what you want to do as a drivetrain in terms of what style you want to use and what type of gear ratio you want to use for that drive. Now, you have a bunch of different drives that you can use. You can use a normal tank drive where you just have wheels on the left, wheels on the right. You can use a mechanism drive which allows you to strafe. You can use a holonomic drive or an X drive where you have wheels on the corners allowing you to strafe as well. And you can use a bunch of different other weird variations that are out there as well. The one I'm going to be covering today is just a normal drivetrain. Pretty simple tank drive. You have all your wheels linear on both sides of your robot, so it's pretty nice and easy for beginners to grasp. There's a bunch of different resources online for other drivetrains as well, but for tank there is a drivetrain catalog that you can use on VEX form, which I'll link below, and that is a great way for beginners to learn what different drive ratios there are out there and what those speeds look like and so on and so forth. So I recommend using that catalog to your advantage. Now, after you and your team have figured out what you want to do, take the design, put it in CAD. In CAD, or you can put it in pen and paper too, but I recommend CAD. You can use a bunch of different softwares such as Onshape, Fusion, 360, or Inventor. All three of those I know have VEX Robotics parts libraries, so that way you can just quickly download parts, edit them, and put them in an assembly and quickly make something. So you've gone through, you've chosen your design, you've made your design in CAD. Now you need to select the materials to build your drivetrain. When selecting your materials, I highly recommend you select C-channels or metal stock or whatever you're going to be using to build whatever item you want. In our case is a drivetrain. You want to use the best possible condition of material. So you want metal that's straight, it doesn't have any holes in it, it's the length that you need it to be, it's the width that you need it to be, and if you need to cut it down, make sure you use some sort of bandsaw. If you don't have one of those, some sort of hacksaw or handsaw that you have to your disposal. And if you have a vise, please make sure you use that. But remember to be safe whenever you're cutting metal, because there's a lot of things that can go wrong, and you can injure yourself easily if you're not paying attention while cutting things. After you cut your pieces, make sure you file them. Again, injuries might be an implication. Also, you can damage field and game elements if you don't have nice, smooth material. And you can easily damage the floor mats, so I really recommend filing things. Lowers injury risk and lowers issues in matches for you. So I have some pieces here for demonstration purposes. So these are some pieces of metal that I've put together to show what framing a drivetrain would look like. Now, you can see here I have two drive rails, both running parallel to each other. Both are very square to each other, both are spaced evenly apart. And I have this 3 wide here that runs perpendicular to this metal. Now, this 3 wide is a temporary piece of structure that I'm using to frame my drivetrain. In framing, I want to just get the basic layout of my drivetrain and make sure everything is nice and square. With this, I'm able to get that result. You can use a 5 wide. Those are also probably best to use for this because you occupy a lot more space, so you have a lot more attachment onto these pieces of metal further along them, so it allows you to get things more square than just a 3 wide. I don't recommend using a 2 wide, but if you don't have a 5 wide, use a 3 wide in that case. Now, You can see how I've attached them. I've attached them with these screws here. These screws are called shoulder screws. With a shoulder screw, it allows it to fit better into the metal. So I'll show you here an example that I have with 2 screws. On my left, I just have a normal screw that I'm going to be using, so normal 8/32, and on my right I have a shoulder screw. So you can see here with the shoulder screw, it has a little shoulder. With that shoulder, it allows me to sit better into the holes. So it's a round hole going into a round object going into a square hole. So I need to fill that space in there, and you can see that I'm trying to move it around and it's not moving. You can even hear it, you can't see it moving. Now I'm going to get a normal screw and do the same exact test. Notice how it moves around a little bit. It's squirming around. So that shoulder screw allows it to sit better into that hole. You can see there. So that's what I'm using to frame my drive. So I have points here and here, here and here. And if you imagine that this goes across to the opposite side and connects the 2 other pieces on that side as well. I want to turn it sideways. Notice how I'm only going through just one of the flanges on the drivetrain C channel. I would recommend going through all the way and boxing that, which I'm going to cover here in just a second. With doing so, it's going to make framing your drivetrains a lot better, and it's going to make sure that you have a better square to attach things onto. So after I've put my temporary structure on, I want to go ahead and put all my permanent support structure on. You want to have at least 2 cross braces on a robot that go from the furthest left point of your robot to the furthest right point of your robot, especially on your drivetrains. It avoids them from being able to flex and move and shift. You always want to make sure that you have the most amount of holes possible for those material on top of whatever face you're attaching to. So you can see here I have 3 holes. I want to make sure that this face, this bottom face or this top face, whichever one is the face that's making contact with my drive rails. I don't want to attach it like this where there's only 1 hole. I want to attach it as such because that will prevent, there's a larger surface area that is occupying. It'll prevent flexing a lot better, and it won't allow items to shift on the robot. So one more thing about using framing. Sometimes support structures might need to be spaced up off of the drive rails, and that's one of the main reasons you use framing. Sometimes you're not able to use shoulder screws for all your support material, so that's why you frame a drivetrain to begin with. With framing, right, and with your supports, you can only frame with shoulder screws if your metal is flush with each other. You can see here that this metal is not spaced out away from my drive rail, it's completely contained. That's because the shoulder can only be so long. You can't have it go all the way down, otherwise you won't be able to tighten your screws. So that's why it's like this. If you have supports, like permanent supports that can be attached directly to the metal, I highly suggest just using shoulder screws for that instead of normal screws. It just makes everything a little bit easier and a little bit stronger. So the next thing I'm going to be covering is boxing. So with boxing, what that is you're pretty much having a stronger connection with whatever you're connecting to each other. So you can see here's some examples that I have in front of you. I have a bunch of different items of boxing and different types of boxing that you can use. So in boxing, you can see here there's a bunch of different ways that you can do so. The way that I strongly recommend is either this type of spacer here. These are 3/8 inch outer diameter spacers at a 7/8 inch length. RoboSource sells spacers that are the exact size that need to go in between a 2 wide C channel. They sell them at a 3/8 inch outer diameter and a 1/4 inch outer diameter, which is right here. I don't have the 7/8 inch, so I couldn't attach it in there. And another way that I recommend boxing is by using standoffs. Now you can see here I have a screw on either side of the standoff, but the 7/8 inch standoff that I got from RoboSource allows a screw to go all the way through that. So you can do so. Just remember that this is a fastener of such. It's a bolt. So when you tighten this, the screw will tighten to this piece of metal, meaning that whatever you attach to the top might ask that you have a wrench of some sort or some sort of nut driver to tighten whatever item you're securing on top of it. Another way you can do so, especially for axles, or if you remember from last year, you had your lever robots. This is a way that you can secure those items as well. So you can have some sort of shaft that runs through here. You can put your shaft collar in the middle, or if you're running a screw joint through here, which I'm going to cover in a second, that will allow you to have a stronger connection point there and allow you to move around that point a little bit better, because with bearings, you're able to get into the very middle of that C-channel. It forces a screw or a shaft to sit in the very middle of the holes that are on the C-channels or in the middle. So, there's another way that you can also do boxing that I don't have available here because I didn't have the time to attach it, but you can use a Keps nut box. So I'm going to show that really quickly since I was not able to make it. So you can see here that I've hand tightened this. Normally what you would do is you'd loosen the top, so that way it's secured to the top flange, and tighten the bottom. So you want to go in opposite directions to allow those nuts to secure to the metal here. And that allows you to get a very thin box in there. But again, I recommend using spacers for this. So you can see here that that 1/4 inch would fit in there just fine. So if you have the option to use these thinner spacers, it's a lot better for you. Now, again, if you have a pivot point for a screw joint or an axle, there's another way that you can do so instead of the bearings, is that you can stack them within a coupler like such. It is 2 bearings attached on top of each other with a coupler that sandwiches on top of that piece of C-channel. So you can see here, here's that coupler, that C-channel coupler, and you can see that these are 2 separate bearings with one on the bottom, one on the top, and when they close together, you have that joint in the middle, not that joint, but you have the space in the middle to attach an item, and you can see that coupler just pops back on there. Everything is nice and secure, and you can secure it with whatever bolts that you want to be using. Again, I'm using Keps nuts because I'm able to just quickly hand tighten them for demonstration purposes. And you can see there, I can stick some sort of longer screw through there, so I'll just go ahead and do so. Here we are, and you can see it rotates pretty nicely around that, and I'll show this one as well. Pretty nice around that point. Now the last one that I want to cover for today is boxing a 1x1 angle. So you can see here I have 2 1x1 angles with one sandwiched on top of the other with 1/2 inch spacers in between spacing them out. So this allows you to get a stronger 1x1 angle piece, or whatever item might have this. It allows it to be a little bit stronger, it won't bend as easily, and it's just better build practice for you to use. For these 1x1 angles, I do recommend taking 3 wides if you have that to your disposal and cutting them down the middle, so that way you have a stronger flange. But if you're not able to, you can also cut down 2 wide C-channel, or also just buy the 1x1 angle pieces from VEX themselves. Okay, so what I'm going to cover right now is a screw joint and how to make a basic screw joint. So the benefit of screw joints is that you use screws effectively for non-powered pivoting items, so wheels on your drivetrain that might not need an axle that goes through them to power them in a motor, or different pivots around the robot that need, movement. So I'm going to go quickly over a cantilevered screw joint right now. So as you can see here, I have a piece of metal here with a screw going through a bearing. Now, there's a few things I want to cover before I explain how to build it. So the reason why I'm not using an axle here to make pivoting items is it sits in the bearing, but it doesn't sit completely well within the bearing. It doesn't fill up all that space in that hole. So it allows it to move around, and also after, you know, continued hits on it, if you have multiple impacts on an axle, it can only take a certain amount of force before it starts to bend. So screws, on the other hand, fill that gap a lot better, and they also have a stronger, you know, a higher tolerance against impacts. So after that, I'm using a bearing here. I just covered shoulder screws talking about framing, so you understand why you would use a shoulder screw instead of a bearing. So it would fill that hole a lot better, but in my case, I don't have any shoulder screws, so I'm using a bearing here to make sure that this screws directly in the center of these holes. So firstly, I want to attach a Kep's nut, as you can see on there, and I've also attached my bearings to the metal using zip ties. It's just to save some weight. You can use aluminum screws and nylon hardware, or zip ties, or whatever is best. I'm using zip ties because it's just easier to attach things. Again, I started with a screw going through here and using a Kep's nut. After that, I'm just going to use a spacer to space away from my metal. You can use any spacer or washer here, as long as you have one between a spinning object and the metal, such as the nut here. It'll reduce friction and also save any issues of destroying gears or metal or anything. Next thing I'm grabbing is a brass 1/4 inch insert. You can see here, it's a hole on the inside for it to slip around the screw, and it spins really nicely once you put a gear on it. I used to use these green inserts a lot for free spin, but once I found out that these were available, I started buying these a lot more. You can see here how much better of a free spin I can get off of them. Whereas with the green insert, let me pop that on. You can see there, it won't spin as long. It has a little bit more friction on there. Whereas with this, again, let me go ahead and... So yeah, they're a little bit better, a little bit easier to spin things on. The next thing I want to do is grab another spacer. It doesn't have to be this big. Again, I'm just using it for demonstration purposes. And remember that you want some sort of spacer or a washer between the pivoting item or the moving item and the metal piece. Now I'm gonna go ahead and screw this down. I screw it down until it's not tight, but the spacer or whatever I'm using can spin freely without spinning whatever item I want to have move. So you can see I went a little bit tight and loosened it. See, it's still a little tight there. That's what I want it to look like. Only loosen it just a little bit more. So there, I have a pretty basic screw joint there. You can see it spins pretty well. It might be a little tight right now, but that's alright. So this is a cantilever screw joint. There are a few other ways that you can go through and make this stronger with that I'm going to cover here in just a second. But you want to make sure that whenever you make a screw joint that you always have the screw attached to the part that's going to be static and not moving. It'll allow the screw joint to actually be a little bit more effective and the screw joint to be stronger. So with it being stronger, like I just mentioned, there are a bunch of different ways that you can strengthen this. One of those ways is where I covered it in the boxing section. You can use this format here to box a screw joint together, so that way it has a stronger place where it's attached to. With the way that I have it here currently, with the screw going through, all its strength is going to be coming from this one flange, this face here that it's attached to. So if your screw bends, which it will because look how long this is, if it's a longer screw, it'll bend out at this point here. It'll damage your metal a lot easier. Whereas with this, look how much more material I have here to work with, how much more the screw is grabbed onto or grabbed into, and I can have my screw joint come off of this left face here. So it'll be a lot stronger in the long run. Again, I also mentioned this sort of boxing as well. You can utilize this type of boxing for this scenario as well if you have that type of item that's moving. Another way you can make this stronger is just not making it cantilevered. So if you have your screw here, you can pretty much attach it into the next piece of metal on the opposite side like such. It's not fully attached because I'm just using this for demonstration purposes, but you can see there that with it on that side is pretty much contained, which is what your drivetrains will look like whenever you're making screw joints for those non-powered wheels. You can also utilize a Kep's nut on the other side to tighten down to this piece of metal. You effectively just put one on one end and one on the opposite end, just like you would for boxing with Kep's nuts, so that way it clamps down on the piece of metal. So you can see here I have one there, and then I put it through the piece of metal that I want to attach, and attach it on the opposite side like such. Now I would attach it just like that, so that way it no longer becomes cantilevered. You can use this for more exaggerated cases, but that's how it would look like in this scenario. Another way to get around having to use Kep's nuts, if you don't need to, or if you need to have more space, you can use a standoff, and you would connect the standoff to that piece of metal. So just remember that the longer your screw joint is, the more it might bend that flange that's attached to. So just remember to always strengthen your connection points. I want to go ahead and bring back that demonstration piece of chassis that I made. You can see here I have my drive rails. I would usually put the screw in from the opposite side, so you can see here I have my screw there. And actually I also have my drive rails flipped, so I have the flatter face facing the outside of the drive. But you can see that I have my screw that would go across, and I can build my screw joint in there and tighten everything down and whatnot. So it would actually look like this. So if you pretend that this is a longer a C-channel for my drivetrain, it would go across in that direction, so that way it's secure. So this is what my typical drive wheel or drive unit would look like if it were attached to the robot. The last thing I want to cover is attaching your motors and attaching your axles. So with your motors, this is what a hot swappable motor would look like. You can see how the zip ties are arranged. I know that teams use rubber bands, and that's fine and dandy, but I highly suggest using zip ties. Although they cost a little bit more than rubber bands and they're not reusable, this is a lot better and a lot stronger to use. In a match, sure, if you need to get around just quickly swapping to rubber bands, you can, but this is the best way to keep your motors hot swappable. And then when attaching your motor, just make sure that it has proper inserts for the motor caps. They have a slight little lip on them, so that way they lock into the holes of a C-channel. Both the 5.5s and the 11-watt motors, so that way it just sits nice and snug. Make sure to put a few drops of Loctite on those screws when you attach it, so that way your motors don't shift around. And whenever you're doing your axles, you can get away with not having to put a bearing on the side that the motor's attached. So for me, that'd be the innermost portion of the robot. And this is for the drivetrain. You can do it for other portions too, but it works best on the drivetrain. So it's up to you whether or not you want to do so. It just saves material and sometimes saves space. But what I do, since my drivetrains are all nice and square and they're framed well, I can attach my motors to the inner portion here, and I can attach my bearings to the outer portion, and I can run my axle across straight into the motor. And because it's going straight into the motor, it fits, and there's a bearing on the outside. It sits very much in the center of the metal, and it doesn't move up and down and shimmy and hit the metal on the inner face, so this inner C channel here. So I'd have my axle going through my bearing, across, out the hole on this side, straight into the motor, and it's pretty much center through that drive C channel.